So in the middle case, since the gravitational force is greater and it's opposite to the applied force, you would take the gravitational magnitude force and subtract the applied magnitude force. And what you end up building is this equation. You have ma equals, this time it's mg minus the applied force. And I mentioned it yesterday, I'll mention it again. Even though the formula highlighted on the left is very similar to the formula highlighted on the right, in the middle, the order in which you subtract actually makes a difference in your final answer here. And by the way, the formulas that I'm highlighting do not include direction. So you would not put negative 9.81 in there. The negative has been taken into account by subtracting. If the acceleration is 0, which means the object is moving up or down at a constant velocity, then the principle going on here is that the magnitude of the net force would have to, well, the net force is 0. I don't even want to talk about magnitude. The net force here in this last situation is 0. And that means that the magnitude of the gravitational force, I wonder if I can fit it in here, must be equal to the magnitude of the applied force and that becomes very simple. In this particular case, what you end up with is mg equals the applied force. And one last thing before we get to the problems. The applied force is sometimes called tension if it's being applied with a cable or a rope. So getting back to question 1, I had a couple of people ask me yesterday why they were getting the wrong answer, because it seemed like such a simple question. They were taking 145 divided by 11 and getting 13.2, which is way off. And it's because they didn't draw the free body diagram. The free body diagram here, if you're going to throw an object, I don't know what it is, it's some kind of a ball, you're going to throw an object vertically into the air, you have to apply an upward force. But if the force of gravity is this big, you're not going to be successful in throwing it. It won't even be off the ground. You have to say that the applied force is greater, so it's going to be ma equals the applied force up minus the force due to gravity. And one final thing. I know sometimes I spend a lot of time reviewing, but I think it's worth it. The final thing is, if this is a written response question, and you need to focus on this, if this is a written response question and all you write is this formula, that is not sufficient. What you should be writing on a written response question for question 1 is essentially everything to the left of that vertical highlight. You should have a free body diagram showing the forces. You should have a statement that the magnitude of the net force is the magnitude of the applied minus the magnitude of gravitational. Then you can go ahead and write ma equals F applied minus mg. All right, does anybody have any questions from this section and this lesson? So first of all, Andrea is asking, is it okay if we just think back to how we added vectors and you're subtracting the smaller from the bigger? And the answer is yes. And in fact, that's what I'm doing in my head. That may not come across as being what I'm doing, but yeah, and I should have said that. For example, Andrea, in the first situation, which is in the first column here, net means add. So how do I find a net force? I add the forces. And what Andrea is pointing out is we're adding two forces that are in opposite directions. So we subtract the smaller one from the larger one. And I really like that Andrea said there's an overarching theme here. And in fact, that idea of taking the larger minus the smaller is the big picture. I had mentioned yesterday or the day before that students who are more successful in high school physics are more successful because they see the big picture. They don't just say F equals ma and throw numbers in. They see the idea that net means total force and they go from there. So Andrea, that's a perfect way to look at it. And let's do number 4. Liam had asked about number 4. So we have an elevator, that should be 10 to the 3, I'm assuming. Yeah, it should be 10 raised to the 3, not 103. It's probably 10 to the 3 on your handout. And we want to find the acceleration, we want to find the tension in the cable under a variety of situations. So first of all, tension is another way of saying applied force. Now, if the elevator is accelerating downward at a particular rate of acceleration, then what that means is that all of the forces acting on the elevator. Oh, is that what got you? So on your handout it says times 103? Okay, I'm sorry, Liam. That should be 10 to the 3. Would you be fine with that question now? Okay. Does anybody else want me to continue with number 4? You know what number 4 is basically evaluating you on are these 3 principles. I believe for question A it accelerates down. So for number 4A, you would use this principle. I believe for 4B it's accelerating up. So for 4B you would use this principle. And I believe for C it's moving at a constant speed. By the way, whether it's moving up or down in question C is not important. If it's moving at a constant speed, you would use this formula. I apologize, Liam. So any other questions at all? All right, then we're going to move on now, and we are going to be looking at a continued application of Newton's second law of motion. So this next lesson is on page 26 of your unit handout, and it's called Applications of Newton's second law of motion, and the objective is to solve problems involving various applications of Newton's second law of motion. So we're going to dive right into the examples. The examples that we're going to look at today will involve inclined planes, but I want to point out to you that what I've told you about how to solve problems using F net equals ma is you must draw a free body diagram and use that to determine the net force, or to determine an expression that you can set equal to ma, because that expression is the net force. And I'm going to tie that to connect it with what Andrea talked about looking at forces in one direction and forces in the other direction. So the first thing I want you to note, and I looked in my PDF file and it was the same thing, is beside question 1 there are your formulas for perpendicular and parallel components of gravity, and it should be cosine of theta. So make sure you are aware that I also copied the incorrect formula into that section. Fg perpendicular is Fg cos theta. Now we are asked to find the acceleration of the mass. And we're going to have to draw a free body diagram. And I could start to draw it if I wanted to. I don't want you to draw anything just yet, okay? I certainly could draw in that there is a perpendicular component of gravity. And I could draw in that there is a normal force that's exactly equal to it. And I'll label those in a second, and we'll officially add them to our diagram in a bit. So I could do that. Now there is, let's see, is there any friction? No, it's frictionless. So you know what? I take it back. We can start drawing these forces in. If there were friction, we wouldn't want to do that just yet. So let's label in what we have here. We have a force of gravity that is perpendicular to the ramp. And if we ever need to calculate it, we can do so because we have that little formula. We take the force of gravity and we multiply by the cosine of the angle. We also have a normal force. And if we ever want to know the normal force, and we will sometimes, we don't have a formula for the normal force, but the normal force is equal in magnitude to the force due to gravity. And I'm just going to put that up here as a reminder to us. I don't believe for this particular question we need to know that, but the force of gravity component that's perpendicular is the same as the normal force in terms of magnitudes. They're obviously not the same because they're in opposite directions, but the magnitudes are the same. There's one other force. The other force is acting down the ramp. What would we call that force? I want everybody to think about what you would call that force. Because let's face it, if it's frictionless, the thing is going to start accelerating down the ramp, so there must be some force acting in that direction. Excellent. It's the force of gravity that's acting parallel to the ramp. So these are the only three forces that are acting on the mass. So if you're asked to determine acceleration, and what I'm about to say is something that I will repeat in Physics 30 a lot. Generally speaking, if you want to find acceleration and forces involved, you're going to end up using F net equals ma. So we're going to have to use the magnitude of the net force equals the mass times the magnitude of the acceleration. And we're just going to say magnitude because we know the direction is going to be down the ramp. When I say down the ramp, I don't mean towards the surface of the Earth, I mean along the ramp. So the first step I told you is to draw the free body diagram. The second step is for you to look at the free body diagram and come up with what F net is equal to. I know F net is always equal to ma, but based on the diagram, F net in this example is Fg parallel. If I add these three forces, and let's face it everybody, F net means F total. So if I add, that's what total is, I add this force, and this force, and this force, all I'm going to be left with is the force of gravity parallel, because when I add Fg perpendicular and Fn, they cancel. There's nothing left. So the first step is drawing this diagram. The second step is coming up with an idea in your head of what the net force is in terms of the diagram. And the final step is to use F net equals ma mixed in with this thing I've highlighted in blue. F net is the force of gravity component that is parallel, and this is equal to m times the acceleration. And again, not to beat a horse to death here, what a horrible expression, but not to repeat myself too many times, but please don't memorize Fg parallel equals ma. Unless you're going to also compartmentalize in your head that that's a formula that works anytime you have a frictionless ramp. And now we can go ahead and do this. Now we can calculate FG parallel on the side here. It's mg sine theta. So if we take the mass, which is 16 kilograms, times 9.81, didn't leave myself enough room here. If we take the mass, which is 16 kilograms, times 9.81 meters per second squared, times sine of 30 degrees, we're going to get the parallel component of gravity. And let's see what we get. Unless you've reset your calculator, you probably don't need to check to make sure you're in degree mode. I get 78.48 newtons. Can I get a thumbs up or anything on that? We're okay. Thank you. So 78.48 newtons is the net force. 78.48 newtons is the force of gravity parallel to the ramp, but that's the net force. So we can go ahead and put that in and set it equal to MA. And if we divide that by 16, we'll get the answer to the question. You get about 4.9 meters per second squared. And it is half the acceleration due to gravity. And by the way, it's half the acceleration due to gravity, Liam, because the sine of 30 degrees is 1/2. And I want to show something to you. You're just one step ahead of me. We didn't, this thing here that we did on the side, I'm going to stop doing that from now on. What I'm going to do instead is take my formula, which is here, and I'm going to put in mg sine theta for the force of gravity parallel. So I'm building a single equation. What we want to move everybody in high school physics towards is not having to calculate something and then something and then something. We want to come up with a formula that you can use to calculate the answer. Now, I'm not even going to put in the numbers here, Liam. If I were to divide both sides by the mass to get the acceleration by itself, I would have my mg sine theta over m, and the masses cancel. This is a very interesting thing, everybody. If the masses cancel, that means you're going to get 4.9 meters per second squared, whether it's a 16 kilogram mass or a 20 kilogram mass. If you had a frictionless ramp and you put two objects of different masses beside each other and let them go, they would both accelerate at the same rate. All right, now let's take a look at the next question. What about if the coefficient of friction is 0.23? So I'm sorry, I want to back up. Any questions with getting our answer here of, I guess I never really wrote it down, the acceleration equals 4.9 meters per second squared down the ramp, I guess we could write. Any questions with getting that answer? All right, now what if, and this is certainly a more realistic situation because, let's face it, frictionless ramps don't exist. So why do we study them? Because it gets you used to the idea of applying Newton's second law. You have to take baby steps, as they say. So what we're talking about doing now is, I'm going to copy this diagram I thought I had. What we are talking about doing now is having the same situation, but now there's a coefficient of friction. So I don't know if you recall, but remember I told you that I really didn't want to draw in all of the forces? And that's because I don't know in question 2, for the forces along the ramp, I don't know if it looks like this. Don't draw this. I don't know if it looks like that. And by the way, if it looks like that, then the answer to the question is the acceleration will be 0. I mean, let that sink in. If the force of gravity trying to pull the box down the ramp is smaller than the force of friction, then it won't move. But if the thing looks like this, then it will accelerate down the ramp. And I need to know the sizes of those forces before I go on. So what we're going to do first, before we complete our free body diagram here, let me get rid of this stuff, is we are going to calculate the magnitude of those two forces. We need to know the magnitude of the force of gravity acting parallel to the ramp, and we need to know the magnitude of the normal force. And one other thing I will tell you here, advice I will give you, is that when you do these problems from here on in, no matter how simple or basic they seem so far, they are going to get complicated. So you need to be organized. If this is a written response, you can't cram everything all in and jump from one piece of the paper to the next. You need to work in a very linear fashion. So what I would do here is I would, in a separate section, calculate, well, we'll do the force of gravity parallel first. That's equal to mg sine theta. Is my memory correct on that? Okay. So I'm going to take, I mean, didn't we calculate this already? Isn't this 78.48? But I can write it down again. This is 16 kilograms times 9.81 meters per second squared times sine of 30 degrees, which gives us the 78.48 newtons. Okay, we can add that to our list here. We know this is 78.48 newtons. Now let's find, and by the way, I wrote F normal here. I don't know why I'm interested in that. I kind of have an idea of why I wrote it, but what I meant to write is force of friction. We need to know the forces acting along the ramp. Okay. So, now, focus here, everybody, because this is complicated. It's got layers within layers. Now I'm going to find the force of friction. Well, the force of friction is the coefficient of friction times the normal force. But I don't have a way to find the normal force except to say, and I had mentioned this over here, look at what I wrote for question 1 in the top right corner of your screen right now. I wrote that the normal force is the perpendicular component of the force due to gravity. Because, and I could actually draw in these two forces right now, the force of gravity perpendicular to the ramp is exactly balanced by the normal force acting on the box. So we're working on the force of friction. The force of friction is mu times the normal force, but the normal force is the force of gravity acting perpendicular to the ramp, so we can use mu times m times g times cosine of theta. Just to make sure that as many of you are with me on this as possible, what I'm highlighting here, Fg perpendicular, is what I'm highlighting here, mg cos theta. So we can go ahead and calculate that. I believe it was 0.23, but I better go back and check. Yep. So we have 0.23 multiplied by the mass, which is 16, multiplied by the acceleration due to gravity, which is 9.81, multiplied by cosine of 30 degrees. .23 times 16 times 9.81 cosine 30. I'll double check my entry here. It looks okay. I get 31.26 newtons. And we can add that to our list. The force of friction, that was the force of friction. This all goes back. If you trace this back through all of the breadcrumbs, it goes back to the force of friction. That's what we were finding. So 31.26 newtons, we can add that to our list. Now, why did we make this list? So that we know how to draw in our diagram the other forces. There is a force due to gravity that is parallel of 78 newtons, and there is only a force of friction of 31 newtons. And we can label these, and we should label them because I'm trying to set you up for success on your next assignment. Your next assignment is going to involve these types of questions. We have a normal force. We have a force of gravity, which is perpendicular. We have a force of gravity, which is parallel. And we have a force of friction. And again, I really hope it's not lost on you that the reason I drew the lengths of those two vectors along the ramp, the lengths they were, is we found that the parallel component is more than the force due to friction. So now we look at this diagram and we say, what will I get if I add all of these forces? Well, if I add, we'll use yellow. If I add the normal force and the parallel component of gravity, I will get 0. Those two yellow forces that I've highlighted cancel. If I now add the force due to friction and the gravitational component that's parallel to the ramp, then I'm doing what Andrea said. We only study so far in this course objects that move along a line. So when you have opposite forces, we subtract the smaller from the bigger, which means our net force will have a magnitude equal to the magnitude of the force of gravity parallel, because that is a bigger force, minus the magnitude of the force of friction, because that is the smaller force. And what that really means, everybody, is if we subtract these two forces I've highlighted in blue, that's equal to ma. Right? I can write ma equals the 78.48 newtons minus the 31.26 newtons, which means the magnitude of the acceleration is that number over the mass of 16. It's not as simple as just looking for a force and a mass and dividing them. You have to know how to find that net force. So what would the net force be? Well, we're going to take 78.48 78.48, and we're going to subtract our answer. I realize I'm not carrying, I am carrying all of my decimals. So that 47.2 on my calculator, that's the net force. And when I divide by 16 kilograms, I will get the acceleration. So the acceleration now is reduced to about 3.0 meters per second squared along the ramp. Any questions with number 2? All right, let's take a look at the third and what I think is the final example. I wonder if I still have it. We'll see if I can copy this. Yeah, it's still there. So we have this situation, but the coefficient of friction is now 0.63. We already know that the parallel component of gravity is 78.48 newtons. We could even draw that in. We know that there is a normal force. Quite frankly, the normal force and the force of gravity perpendicular, I don't care what they equal because they cancel out. Right? We could put them in as numbers, but I'm not going to. So I'm going to put in that we have Fg parallel, which has a magnitude of 78.48 newtons. We also have a normal force. We also have a gravitational force component that's perpendicular. And we have a force of friction. Let's calculate the force of friction. And I'm going to go through this again, even though we could just look back at how we did it in the previous question. The force due to friction is found by taking the coefficient of friction times the normal force. But on an inclined plane, the normal force is equal to the perpendicular component of gravity. And the perpendicular component of the force of gravity is mg cos theta. Please, I'm pretty sure that's right, but with perpendicular it's cosine? Okay. So now what we're going to have is we're going to have 0.63 times 16 kilograms times 9.81 meters per second squared times cosine of the 30 degrees. And I don't know exactly what we get, but because I wrote the question a particular way, I know that this number is bigger than 78. That's the point of this third question. So let's see, 0.63 times 16 times 9.81 cosine 30 gives us 85.6 newtons. So what that means is that if this force of gravity parallel to the ramp is 78 and the force of friction is 86, it's bigger. The force of friction up the ramp is bigger than the applied force by gravity along the ramp. And I don't even need to write in what this number is. Since the force of friction has a larger magnitude, the answer to the question is the acceleration is 0 meters per second squared. You have to use some common sense here. Don't blindly look at that diagram and say ma will be the force of friction minus the force of gravity. So Andrea, this is one case where you wouldn't just subtract the two numbers. Right? What was this, 86 newtons? The net force is not 86 minus 78. The net force is 0. The force of friction isn't something that can actually pull the box up the ramp. And that's the answer to question 3. So any questions with that final example? All right, so these get a little difficult in the questions. I just want to spend a minute here going through a couple of them. If you look at number 1, number 1 is the same as the set of examples that we did. Okay, you should have no problem with that. However, when you look at number 2, it's entirely different. Let's talk about the setup for number 2. If you have an 80 kilogram box along an incline and you want to move it up the ramp, if there's no friction, then it will slide down the ramp because there is a parallel component of gravity. If you want to push it up the ramp, then you have to apply, this is an applied force now, then you have to apply a force upwards that's at least as big as the parallel component of gravity. Which means that in this particular question, the applied force, this is for number 2A, the applied force upwards, which is what you want to find, will be the same as the gravitational component that's parallel to the ramp. If you apply a force up the ramp smaller than it, it won't accelerate up. In fact, it will accelerate down if it's frictionless. Before I move on and talk about the next part of this question, I need to make sure that you understand the significance of what I'm saying here. Does anybody have any questions about the diagram for 2A? Now there's no friction. 2B, I believe, says there's friction. There's a coefficient of friction. So wait a minute. If I push, forget about this force down the ramp. If I pull the box up the ramp, and I look at the forces that are acting down the ramp, this time there are two forces acting down the ramp. There is a force of gravity parallel to the ramp, but there's also a force of friction now. And friction is acting now down the ramp because I'm trying to push the box up. Now things all of a sudden elevated to an entirely new level. Look at the lengths of these arrows. Look at the length of this arrow, which is the parallel component of gravity. Look at the length of this arrow, which is the force of friction, and look at the length of this applied force. Would I be successful in moving the box up the ramp? No. Because when I look at these two forces added together, look at the total force that we're talking about here. The total force that I have to overcome is Fg parallel plus Ff, which means that in question 2b, I need to apply a force that's equal to the sum of those two forces. So I'm going to give you guys about 20 minutes to a half an hour here to work on these problems. They are certainly more complicated than things we've dealt with so far. There's only 3, but it's going to take you a while for some of these. I'm going to check in on you in about 10 minutes, even if you didn't have any questions, and I'm going to ask everybody right now to do a check-in with me in terms of too fast, too slow, just right.